question on the quiz. I don't have a copy here, but I already posted the solution to the quiz in Canvas, right? So you can refer to that solution. Make sure you can make it right next time. No questions by far, right? Okay. Let's get into transistors really quick. Then we will do the layout, the cross-sectional view for the transistor. But we need to understand what's going on for the transistors first. So let's look at the N-type transistor first. It's called NMOS. So MOS means MOSFETs, right? This is metal, oxide, semiconductor, N-type, and this is called gate, drain, source. So source means the source of the electrons. So electrons flow from the source to the drain. draining electrons from the source. So current flows from where to where? Drain to source. Right? So the voltage drop should be from where to where? Voltage drop. Come on. Electrons from source to drain. Okay? Current from drain to source. So voltage drop from drain to source. Right? Makes sense. So in that case, you need a positive voltage drop from here to here in order to push current from drain to source. But basically what's really going on physically is electrons are flowing from source to drain. That's how that works. Okay, and gate is providing a electric field from the gate to the substrate. Looks odd, it's just a symbol, but if you flip it, rotate it, this is basically a transistor. All right, let me draw it here. And cross-sectional view looks like this. Gate. N plus or P plus? Yes. So drain, source, usually you have a little metal contact like a via or something, got a wire on it, and we usually short source to ground, for example, for the first example we're looking at. And we need the gate. The gate here, what's the material for the gate? Polysilicon, right? There are some of the technologies that do metal gates, which is fine, but C5 is polysilicon. And so we need a voltage drop here, ground it. We call this VGS. Keep in mind, VGS has to be larger than VTHN, which is threshold voltage. To turn on the NMOS. Keep in mind, it's VGS, not VG. It requires a voltage difference from G to S, not just a VG. And you also need a drain to source potential drop. I'm just drawing the ground over here, but you should know that in all the circuits, if I draw a symbol, ground symbol, they are what? Shorted together, right? So it's basically from D to S drop. It's called VDS, okay? Which is providing that driving force to push the electrons or attract the electrons to the anode. So the way that works is because you are applying a positive voltage across VGS, so it's creating a electric field which attracts electrons in the P sub. Electrons are free electrons, even though there are not too many. It's a P type, right? But there are still free electrons. So free electrons will be attracted underneath the channel to form a channel. It's called a channel, the electron channel, right? But it's static, nothing's moving. If you only provide a VGS but not VDS, there will be only a electron channel being formed underneath the gate, but nothing is moving, all right? Whenever you apply a VDS across DNS, this is a positive voltage over here, so it's going to attract electrons to the drain. And now it makes sense, right? So it's draining the electrons from the channel. So it's basically flowing from the source. It looks like it's from the source. So from here to here, right? So it's going to keep moving that way. So you can see this is a PN that reminds you about what? PN junction. So PN junction is the diode. If you forward bias it, what's going to happen? Whenever this is larger than 0.7 volts, for example, it's going to flow current into it. Forward bias it, because this is a diode, right? It's going to run current from left to right, but not right to left. So in that case, what's going to happen is, for example, I have a little P tap over here. I'm going to explain this why we have this one over here in a bit. If the little parasitic diode being formed over here is getting forward biased, what's going to happen? You can see there's a diode here, right? It's a PN junction. Just in case your substrate has a little voltage, for example, it's not 0 volts, like 0.7 volts or 1 volt, and this N node is grounded, what's going to happen? That's awful, right? Why? Think about it. You got a voltage on your ground, yes. For example, the P sub, right? The P sub is like one volt, and the wafer itself is 1 volt, and your source is grounded. So N-type semiconductor material is grounded. So in that case, it's forming a diode, and it's being forward biased because the P sub has a higher voltage. So what's going to happen is it's going to flow a current into source, and eventually it flows into the channel. Or you can also consider this as electrons are being attracted into the diode. Isn't that the same process? When you run current through here, it's basically electrons going back. So what's happening is you are losing electrons in the channel. So this VGS spends so much time and efforts to form that electron channel, but this P sub is just draining the electrons from the channel, okay, making the channel thinner. So it's not open anymore. So it's not on anymore. It's maybe off, at a lower voltage of the VGS. So it turns out that you are having a higher threshold voltage. Does that make sense? It's a super important concept. Can anyone explain this really quick to me? If I have a voltage to P sub, for example, 1 volt, and then you are having a higher threshold voltage, why? Anyone can explain from beginning to the end? If your P sub for the N modes, the P sub is not 0 volts or has a higher voltage than 0.7 volts, it's going to forward bias that PN junction. Then it results in a higher threshold voltage. So what we want to do? Do we like it? No. Higher threshold voltage means you need a higher voltage to turn it on. Okay, especially for this low voltage technology or very small technologies, you need like just 1 volt to turn it on. So the threshold voltages are around like 0.3 volts. So how to do it? Ground substrate how? At the back of the wafer? No, there's no way to do that, right? Like you welding a wire on the back of the wafer at the bottom and looking at the bottom of the wafer? No. It's a P-type, right? You want to ground the P-sub. You just want to ground the P-sub. Or you can say, I just want to connect the P-sub to the lowest potential of the circuit, or the entire circuit. Does that make sense? I never want a higher voltage or a limit voltage to the P-sub because it's gonna, very likely it's gonna form a diode. Forward biasing diode. I never want that parasitic diode to have a higher voltage than 0.7 volts anywhere. So in that case, I want to ground the P-sub. How do we ground it? We have to implant a P plus in the P-sub because everything is bottom up precise. So if you put a P plus in the P-sub, it's actually internally shorting to the P-sub, even though it's not exactly P plus, but they are both P-type. So they are shorted. They are shorted to each other. Okay. So in that case, you can have a via, right? Just connect to the top, bottom up, using via 1, via 2, via 3, and to connect to metal 3, and you have an opening on the top of the chip, and you short it to ground. So in that case, you can ground your P-sub, which is critical. So you are not having any forward biasing or forward biased diodes. So you can keep your threshold voltage in a reasonable range. And if you don't short your P-sub to ground, and it results in a higher threshold voltage, and this effect is called body effect. In the interview, someone probably will ask you, hey, explain what body effect is. So how to explain that? Right, the body of the NMOS is not shorted to ground, or the lowest potential in the circuit, resulting in a higher threshold voltage, which is called body effect. Make sense? Question on this? And a lot of times in cadence, this little material or this little part in the library is called P-tap. P-tap. So in the NMOS, for the NMOS, you need the P-tap. Okay? Let's look at PMOS. Oh, we haven't gone through the curves yet. So let's look at the curves. So for here, after it forms a electron channel, and you have a VDS, keeps increasing VDS, what's going to happen is, so when VDS increases, VDS increases, the channel I can also draw it this way, right? Doesn't matter. Same stuff. So whenever you increase the voltage and it starts draining all these electrons, and this channel becomes this. The shape changes. It's really interesting. So the electron channel looks like this because all the electrons are being attracted to the drain. So it becomes like a triangle shape. And if you keep increasing VDS, this layer will keep retreating. It goes like this. So the thing is, whenever the layer of the electrons is still have overlap between here and this shape and this N plus, the current, since we care about the current a lot, so the current going through the channel still goes up. Okay, but whenever it reaches here, this point, it's called pinched off. It's called pinch off. Got pinched off. So that means it's the current got saturated. But you probably have a question. So whenever it got pinched off, it looks like the electron layer doesn't have any direct contact with the N plus anymore. Why it still has electrons going through it? Let me draw a bigger picture over here. Yeah, just in the micro environment, it's just a little bit different from whatever you have experienced in the bigger world, you know. So it looks like this. I'm not drawing that p-type anymore, just showing a bigger picture here. Ground here. And VDS. So after here, right, this is electron channel. It keeps going. If you keep increasing this guy, it moves through here. So there's no overlap anymore, but Y still has current going through it. The reason for that is because it's a super small area, right? So the electrons will tunnel through. So these electrons will go through this area and reach the drain terminal and goes back to the ground. So it's still able to circulate these electrons in the circuit. Still runs current. But after pinch off, so this point is called pinch off. After pinch off, when you increase VDS, the current value is not increasing anymore. It's almost saturated. So the curve looks like this, ideally. Okay, VDS, IDS. So IDS is current going that way, which is electrons going this way. Okay, IDS. It's called VDS versus IDS. Is one of the IV curves we care about. It's going to be on the quiz. So it looks like this, ideally, and this should be flat. But in real life, it's not flat. I can show you. You know, usually if you look at the data sheet of this MOSFET transistors, look like this. But we usually don't care about this area. Okay, we only care about usually it's being used. This area is being used because it has a super high internal resistance. So this area here is called linear area. Linear, and this is saturation. So this happens after the pinch off. It saturates, even though the layer still moves like this. After this pinch off point, it's still increasing VDS, so the layer moves to the left. But the thing is, the current, when you increase VDS, IDS is almost flat. This is called saturation region because the current gets saturated. But however, whenever it's still over here, right, the channel starts from here, right, and keeps moving up. So in this region is the linear region. So the current increases quickly. Whenever you increase VDS, the current increases very quickly, and this is called linear region. It's almost like a resistor with a certain resistance because of the linear, right? If you do a derivative of the V over I, or I over V, you can definitely find out the resistor, and that resistance is definitely lower or higher than this resistance. Just let me know which region has a higher resistance and why. Saturation has a higher resistance because this is the V, right? If you draw that slope over here, you get a super long V and little tiny I. So eventually you are getting a very high R. But over here is the low resistance. In a lot of cases, if you're basically an NMOS transistor is what? It's a VC VS. What does that mean? It's a voltage control voltage source. Voltage control voltage source. Oh, sorry, voltage control current source. Okay, the voltage control current source. Voltage control means that's the VGS controlled current source. Why is the current source? That is why it's a current source. Current is not changing, and it has a super high resistance, internal resistance. That's why in your Thevenin's equivalent circuit, whenever we are dealing with current sources, we do what? A lot of information. It's all connected. In Thevenin's equivalent circuit, when we are dealing with current sources, what we do with it? Disconnect it. Why? Because it has a super high internal resistance. So in order to become a current source, okay, so first the current shouldn't change. It's a source, right? If it changes, it's not a source anymore. Okay. Second, it need a it needs a really high internal resistance. So that's why it's very simple. It's not really high quality current source, but it is a voltage control current source as an NMOS transistor. And we usually use a saturation region for that purpose. Okay, and this point, the voltage value here is called VDS set. You'll see this parameter from the textbook a lot. So it's a VDS, yes, it's a VDS value on the VDS axis, and the saturation point. It's called VDS set. And this equals VGS minus VTHN. Something you need to know. Okay, so we have three voltages. What is this one? VGS. What is this one? VDS. So we need both voltages to run current through this through this device. So what are the two voltages? VGS and VDS. Okay, we are looking at the IV curve for VDS versus IDS. It looks like this. Keep in mind, you just have to know this. Graduate as a computer or electrical engineer, just have to know this. Okay. So we are not considering the VGS effect here yet. So if you're adding VGS to it, what's going to happen? It's like this. Until here. All right. So this is VGS 1, VGS 2, VGS 3, sorry, VGS 4. Because this curve doesn't have a dimension for VGS, but the thing is, it's running behind the scene. If I give a VGS 1, for example, it's a bigger VGS, like 5 volts, it's going to run the curve like that. 3 volts, 2 volts, 0.5 volts. It's not working, providing a super low current. And this region is called, this region is called cutoff. It's a cutoff region. It's basically off. Why? Because VGS here is probably lower than 0.8 volts. So now you know that for the C5 technology, the threshold voltage for the NMOS transistor is what? 0.8 volts. Close to that. So that means you need a VGS to be at least 0.8 volts to turn on that transistor, and then you apply a voltage across the drain and source to run current through it. So that's how you operate this NMOS transistor. You need to know this IV curve, and you need to know another IV curve. I'm going to show you really quick. Okay? Any question on this for now? You need to know these things, okay? First, body effect. You'll be on the quizzes. I'm going to ask you, like, what is body effect? So body effect. Okay? What is body effect? One more time. Starting from where? The P sub is not grounded. If the P sub is not grounded, you have issues. There will be issues. Okay? What is the issue? You are losing electrons from the channel, which results in a higher threshold voltage. It's getting more difficult to turn on that NMOS transistor. That's called body effect. IV curve, VDS versus IDS. There's a VDS set. You got saturation, which has a high internal resistance. You have a linear region, has a low internal resistance. You have a cutoff region whenever VGS is lower than 0.8 volts. If you have higher, whenever it's in the saturation, you can have different VGS. You know, lower VGS will give you a lower IDS. Higher VGS give a higher IDS. Okay, now let's look at pinch off. What is pinch off? This point is pinch off. Whenever we increase VDS, it got pinched off at this point, and then keep moving to the left, it enters the saturation region. Why electrons still go through? It tunnels through this line, okay, because of the electric field. Any questions? No? You're good? Okay. Now let's look at the VGS over, versus IDS. Now let's do a VGS over versus IDS. So just find out, we just care so much about IDS, right? Why? That's the whole point. NMOS transistor is performing like a switch, right? Whenever it runs current through itself, the switch is on. Whenever there's no current, the switch is off. So we care about the current running through it, through the channel. So now we are looking at the effect of the VGS versus IDS, which is the channel current. And it works like this. So this is VTH, and that's 0.8 volts. After the threshold voltage, you get current going through. It works like this. So apparently, you got higher VDS. This is VDS 1, VDS 2, VDS 3. Wait. Did I? Higher VDS. Which one is higher? Which VDS is higher? Which VDS is higher? So from here, even though I have a fixed VGS, I'm looking at VDS. But we know that no matter which one is higher, as long as it's getting higher, you get a higher current, right? Doesn't matter, it's a gate, VGS or VDS. So higher VGS will give you a higher potential to drive more current through the channel. Higher VGS will open that gate or the channel bigger, and so you have more electrons in the channel. So whenever you apply the same VDS, it drives more current through it. So for here, which VDS is higher, you think, in this VGS versus IDS curve? The first one is higher. Why? Because the same VGS, this guy is giving you a higher current, right? Lower and lowest. So this is the biggest, largest VDS. Make sense? Okay. So if I give a quiz asking you to draw the VDS versus IDS and VGS versus IDS, can you do that? Right, just do this. This is what? This is what? Yeah, it's that simple. Let's look at PMOS. For PMOS, okay, so for PMOS building the N well, so PMOS has to be building the N well. Why? Because the P sub. If a P-type substrate, you cannot directly put your P plus in the P sub. It's shorting to ground. You're asking why? I don't want to short my P sub of my PMOS to ground. Is that possible? Do you know what I'm saying? Since it makes sense that P plus will be shorted to P sub because they're the same material, they're shorted. So that's why you need an N well in between them to isolate this from this guy, okay? And the thing is, why do I have to short my P sub of the PMOS to ground as well? Remember when we come back to this point? NMOS, we have to short P plus in NMOS to ground in order to avoid body effect. So P sub is shorted to where? Ground. I don't want to short my P sub with the PMOS to ground. Is that possible? No, it's just one wafer. You get billions of NMOS and PMOS on the same wafer. So P sub is shorted to ground. It's permanently shorted to ground. There's nothing can change it. I'm going to draw NMOS for you here. It's grounded. Can I change it? You want to crack it? No, it's just one wafer. Okay, it's one chip. So P sub is always grounded. That's something you have to know because you have NMOS on the same wafer as well. That's why it's called CMOS. Complementary. We need an NMOS, PMOS on the top and NMOS at the bottom to form an inverter from the logic. Right? That's a NOT gate inverter. A NOT. And we need a PMOS on the top and series NMOS at the bottom to form an AND gate or NAND gate. Okay, so all these gates are formed by transistors and are complementary transistors. That's why it's called CMOS. So in the old days, they used NMOS logic. That was in the 1970s or earlier. They do this, resistor and NMOS to form an inverter. Why? Because it's using, they're using pull-up resistors. VDD. If you turn off this guy, this is being put up to VDD. This is getting 5 volts, right? It's inverting. 0 volts input getting a 5 volts output, so it's inverting. And if you have a 5 volts, it turns on, so this guy being put up to ground, so I'm getting 0 volts. It also works, but what's the problem? Come on, resistors, like NWell resistors, you're serious? Can probably only integrate like 1,000 NMOS transistors and resistors on the chip, taking a huge area. So that's why we moved into CMOS. Starting from the 1990s, I believe, or 80s probably. So everything is CMOS right now. No NMOS logic anymore, keep in mind. That's like almost 50 years old, 60 years old technology. So this is modern CMOS, okay? So CMOS, we have both. So in that case, P sub is always shorted to ground. In that case, we need an NWell to isolate the P plus from the P sub, okay? So it's not shorted to ground. If you short the two PMOS nodes to ground, it doesn't make sense, right? It's not doing anything. So in that case, we need a N type as well for the similar purpose. So it's N plus in NWell, and this is called N tap because tapping into the N body. So NWell is the body of what? Of the PMOS. So P sub is the body of the NMOS, and NWell is the body of the PMOS. Sometimes it's called body, sometimes it's called bulk. Or bulk. Okay, it's the same stuff, right? It's just a substrate holding that device, right? It's holding that device. So in that case, N plus should be shorted to where? Why? Why do we have to short it to somewhere? Have to understand why do we need an N tap? Why do we need a P tap? We already explained that to avoid body effect. So now here we need an N plus in the body of the PMOS. We want to avoid body effect as well, but how and why? So for PMOS, the way we operate it is we need this is for example source drain. Okay, so we need a positive voltage from source to drain, to gate, and we need a positive voltage from source to drain as well. So what's going to happen is you can see source to gate No, it's not VGS anymore. Keep in mind, it's VSG. Has to be larger than the threshold voltage with VTHP. And some of the textbooks using negative numbers, I don't like it. And you can see our textbook keeps using positive numbers, but we flip GS to SG. Same stuff. So we can keep using a positive threshold voltage for the PMOS as well. So eventually this is a little bit higher. The reason for that is the mobility of the holes are lower than the mobility of the electrons. But you guys need to understand, especially in the interview, holes are not moving, right? It's just a concept. The mobility of the holes are lower or slower than the mobility of the electrons. Okay? But holes are not moving. Because you can see this one, this negative voltage here, the cathode of the battery applied to the gate instead of an anode applied to the gate. So you can imagine this electric field will attract holes into the channel. So there are holes in here being attracted. Okay? And then I apply a potential difference between source and drain. Source and drain. Higher, lower. Okay? So what's going to happen? What's going to happen? What's physically happening? What is physically happening here? High, right? High, which means the electrons are going to move in that direction. So basically what's happening is electrons moving in that direction, they're filling up the holes over here, and it seems like the holes are moving in the other direction. The holes are taking positive charges, carrying positive charges. So whenever electrons moving in this direction, because of the electric field, we have a battery here. So anode is definitely going to attract electrons. Electrons moving in that direction, so holes are moving in the opposite direction, even though they're not moving. Look, you are joking. But you know what I'm saying, right? That's just a concept. Even though they're not, relatively they are moving, but they're not physically moving, right? So the thing is, electrons are moving in this direction, and the same as the currents are moving in the opposite direction. This is something you can understand. We learned this from circuit 1, right? So you have a higher potential for S, lower potential for D, so current flows in that direction. That's how that works. So you apply a voltage VSG over here, which is lower than higher than 0.9 volts, the threshold voltage for PMOS, and then it's going to turn on the channel by attracting holes and forming a hose channel, and then drive the hose to the left to form a current flow. Okay, so definitely it's forming a diode over here because the P is a P plus and it's an N-well body. It's an N-well body. So it's forming a PN junction, which is the diode over here. So which means the N-well needs to be shorted to where? Like a diode. I want to always reverse bias it because I don't want to run current through it. It's not a design. I didn't design this diode. I can design a diode. I can do it, but this is not a diode. It's a PMOS. So I don't want this diode to work. How? Reverse bias it. Give a higher potential here, lower potential here, so no current is going to run through it forever. So how do we do it here? Oh, put an N plus in the N-well to form an N-tap. Okay, so short it to N-well. And then I'm going to have a wire via, and then short it to VDD. Or, aka, the highest potential in the circuit. So your diode is never get forward biased because your cathode is having the highest potential in the circuit ever. Right? So you can see N-well for the PMOS is shorted to the highest potential of the circuit, and P sometimes it's called P-well, but there's no P-well at all. It's a single well process. You should understand that there's no P-well. Okay? P sub is a P-well, even though there's no P-well, but we just call it P-well sometimes. Okay? P sub is a P-well, and so the P-well should be shorted to where? The lowest potential of the circuit for the NMOS. Okay? So here's the inverter circuit in the symbol. And for example, this is your NMOS and PMOS. Can you make a inverter circuit from this? Of course. Yeah, just make the certain connection, gate to gate, right? Like gate to gate. Just short the two gates. Short the two gates. And drain source getting shorted. So just like this. Short it. And then you can drive, connect this to VDD, connect this to ground. Okay, then that's inverter, right? Pretty simple. Any question on this? Okay, take a look at the IV curves, see if you can do the IV curve. Let me see if I covered everything about the quiz. Okay, it's a really simple quiz, right? Just based on all these kind of things. I'm going to do a really quick review. Guarantee that you are learning something, have some takeaway from this class, okay? So let's see, IV curves, doesn't matter as NMOS or PMOS. For PMOS, just change this one to VSD for PMOS. Change this to VSD. Change this to ISD. It's the same stuff, okay, for PMOS. Here as well, VSG for PMOS, okay? But nothing else other than that. It's the same curve, same types of curves, okay? So where's VTH? For PMOS, it's going to be VTHP. For NMOS, it's going to be VTHN. So that's the threshold voltage. So what is this voltage? VDS set, saturation point voltage. VDS set. If the PMOS is a VSD set. Okay? Which one has a higher voltage? Okay, so VGS to IDS, it looks like this. Okay, VGS to IDS, and threshold voltage is over here. And for resistance, I explained to you guys already. Resistance, which region has a higher resistance? Saturation region. Why? Because of the slope. Here you can see. Any questions on this? No? Take one quick look at this one. I know you guys are pretty bad at this, so. Expect a quiz next week, okay, on this again, one more time. So how do we draw it? P-select is what? Is P-select doing anything? Yes, it's just to avoid misalignment. But actually it's not the area for dopant. So how do we draw it? Sub first, right? Then what? This guy's doing what? Do we have a poly? Not really. So it's gonna be a N-select means this is inactive, right? P-select means this is P-active. What is this? Should be Fox, right? Should be Fox. What else? You have poly? Nope. The metal one? Yep. You got a via. Another via. I got a metal one. You got a metal one. That's it, right? Okay. See? Same. This one, I'm gonna just let you look at the answer. Just one more practice over here. So, contact is a via, poly, right? Poly layer. Got P-sub, Fox, poly, via, metal one. Easy, right? Okay, so whoever lost the points from the quiz last time, make sure you review the examples recorded, right? Just review these two examples, and there are a couple examples from chapter 4 and chapter 5 of the textbook. Make sure you can get 100 on another quiz anytime next week. I don't know yet. but I do find issues from your quizzes, so just want to give you more practice on it. So now let's do the quiz today. See if you paid attention to the lecture today.